Anyway, thanks for being here, you guys. I'm really happy to see you guys. Thank you for coming. Yeah, Wednesday was a sad day for our campus and community. It was also a scary day. Not knowing exactly what was going on. Seeing law enforcement kind of in full force around campus. It's definitely unnerving. So everyone responds differently to tragedy and scary events, and whatever your reaction to these events, you're not alone, and you're not weird or whatever for feeling the way you feel, even if that response is that you are unemotional or unaffected. That is also a normal response, and not something that you have to feel bad about or anything like that. Or the people around you might be feeling a certain way or responding a certain way, and the way you feel is completely valid, whatever it is. As some of us, as we try to heal together as a campus and community, just remember that we're all kind of in this together, okay? And I as a teacher have the luxury of being able to offer a different makeup time for the final exam, for any of you who want to delay taking the final. That's a luxury I have because I also teach through extension, so I have some classroom space available. That's not a luxury that all teachers have, and with just logistics, I know a lot of professors wish they could make some sort of accommodations for their students, but just it was not logistically possible. And so I don't want any of you to have any negative feelings or bitterness, or question why some of your other professors may seem less caring, and I don't think any of them are any less caring than I am. I know I oftentimes gush about you guys as students, but I know all of the professors here care very much about the students, even if they're not as vocal about it. And so, during scary events, maybe it's always hard to know what is the best thing to say or do. And so if a professor seemed maybe callous or whatnot, it was I can assure you it was certainly not with malicious intent or any intent to scare students or anything like that. Just it's always hard to have wisdom in all situations. So anyway, we are all in this together, and we are working together to heal and also grieve together. So anyway, again, I'm just thankful for each of you as students. I'm thankful that you guys are able to come and be here. And so anyway, thanks. So, as far as the lecture content I wanted to cover this week, it was all going to be a review, or it is all review in preparation for the final exam. I just want you guys to feel as comfortable and ready for the final exam as you guys can be. I have posted a practice final online that I feel is very helpful and representative of what the actual final exam will look like. It largely consists of kind of a paragraph describing some kind of situation where you can do statistical inference, and then it asks questions related to the appropriate inference method. So things like what are the hypotheses, what are the test statistic and all of that. So that will cover a large portion of the final. You will have some conceptual questions, and I tried to cover a lot of those conceptual topics in the video that I recorded and posted on Wednesday as well. Okay, so if you have the time to view that, I recommend watching that. There will be a few questions on the final that are very similar, in my opinion, to questions that were in that video. So as far as today's stuff, I want to do kind of just a very broad recap of the course of statistics and kind of some big picture things, how everything kind of fits together, and then I'll spend some time just kind of reviewing the process behind confidence intervals and hypothesis testing. This is not new stuff. It is intended to be a review, and just I hope you'll all feel ready for the final when you guys take it. Okay, so let's kind of do. So I think on the first day of class, I asked, why do we study statistics? And I don't know if any of you guys remember the answer that I gave, or what this was, and I said it. I kind of broadly said it. Well, it's to help us understand the world around us, and I would argue that that is very much the grand purpose of education and studying any subject, really. But in statistics in particular, statistics allows us to make conclusions about the world or about the population, conclusions based on limited data. Okay, and these past couple weeks have focused mostly on statistical inference. And as far as statistical inference goes, the idea is, we observe and study a sample, okay, and based on what we see in the sample, we make conclusions about the population. Okay. And the way we do this often depends kind of on our understanding of sampling distributions, or we say, we ask, how likely are we to observe the data I have if I make certain assumptions about the population. Okay, and so that would be, this is kind of like finding the p-value. Okay, and all of our calculations there are based on our understanding of the different topics we covered in our class. So the course overview as a whole, we started off learning descriptive statistics. So descriptive statistics is, how we describe our sample of data with, a few summary numbers. So we're describing our data with some summary values. We also learned how to display them with graphic displays and things of that nature. But kind of that whole first, the whole first midterm was just on descriptive statistics, and included in descriptive statistics is describing data when you have two variables, and that was where linear regression came in. Okay. And then the second midterm covered probability. Which tells us how likely or unlikely events are. And then, once we got a hold of probability, we looked at probability distributions. We had the normal distribution there. And then once we understood probability distributions, we got into sampling distributions. Which tells us how likely or unlikely particular sample statistics are, or these summary values that we learned about in the descriptive statistics. Sampling distributions tell us how likely or unlikely particular sample statistics are. Okay, and then we bring those two concepts together, descriptive statistics and our understanding of sampling distributions, to get into statistical inference. Which is all about, observing and studying a sample, and based on what we see in the sample, we make conclusions about the population. We can do that because we can answer questions about the sample statistics that we see based on our understanding of sampling distributions. Okay? And as far as statistical inference goes, there are kind of two methods that we covered here, and they are confidence intervals. And as far as confidence intervals go, we covered three types of confidence intervals. We have confidence intervals for P, the population proportion. We have confidence intervals for mu, and confidence intervals for the quantity mu1 minus mu2, the difference between population means. Okay, and then we also have hypothesis tests. And we have hypothesis tests for P, for P1 and P2. So two proportions, two populations and their proportions. Hypothesis tests for mu, and hypothesis tests for mu1 and mu2. So means and two means. So we skipped the confidence interval for the difference P1 and P2. If you can do confidence intervals for mu1 and difference between mu1 minus mu2, you can do confidence intervals for p1 minus p2. I'm not going to put p1 minus p2 on the final or anything like that, but if you encountered it in the future in some other context, if you remember anything about confidence intervals over here, you can do it for this other stuff. Okay. So we have kind of like 7 different topics as far as statistical inference goes. If you take additional statistics courses, and it's always a little bit of my hope that some of you guys will, you know, you'll probably learn some other statistical inference methods, including ANOVA or chi-squared tests or things like that. You know, if you have the full textbook, you can look ahead to some of the other chapters, chapters 10 and so on and so forth, and it might you know, cover some of these topics as well. But you know, within our 10 weeks, we get up through chapter 9. I feel pretty good about that, and this is what we've covered as far as statistical inference goes. But you know, wherever you have data, there's probably some kind of statistical inference method that can be applied to the data, and so it's a limitless field, guys. All right, let's talk a little bit about well, I don't know. So in the Wednesday video, I emphasized that it is very important that we know which of those 7 methods we're going to use, whether you have so I'll just write you know, it is important that you know if you have 1 sample or 2 samples, and if you have proportions or means. Okay, and I covered this a little bit in the video I posted on Wednesday, talking about, you know, how to answer this. So you're gonna, for determining how many samples you have, you need to kind of see how many n's you can identify. Do you have 1 n or 2 n? That's really going to be the key there. Okay. And proportions or means, I provided some keywords. You know, obviously, if the question talks about proportions, you got proportions. Or if it mentions averages or means and standard deviations, then you're dealing with means. Okay. Another key thing is that if you have proportions, you will always use the z, and if you have means, you're always going to use t, and this is always going to be the case. Okay, so you've got t and you've got z for proportions and means. Is that okay? All right, so I was just going to kind of run through concepts for, you know, confidence intervals and hypothesis testing. So let's talk about confidence intervals. Okay, and so all confidence intervals are in the form of, you know, you have the center of the interval, and then you go plus or minus a margin of error. Okay, this is always the form of a confidence interval. At the center of the interval, you will always put your best guess for the parameter based on your data. Okay, so in some courses they call this thing the point estimate. It's the estimate of your parameter based on your data. Okay, and then you have plus or minus, and then the margin of error always gets split into a critical value times the standard error. Okay, so for our different confidence intervals, so if you're making a confidence interval for the population parameter p, your point estimate, or your best guess for what p is based on your data, is p hat. This is our best guess for what p is based on the data we have. With proportions, our critical values are always going to be some z value, a z star. And the standard error is p hat times 1 minus p hat over n. For mu, we are trying to make a confidence interval for the population mean mu. We will put x bar as our best guess for what that is. That's our point estimate. Okay. Plus or minus the critical value, now that we're dealing with means, comes from our t distributions. We've got t star. You look that up in the table. And our standard error is s over the square root of n. And then lastly, we have for mu1 minus mu2. In the center, we're going to put x bar 1 minus x bar 2. This is our best guess for what mu1 minus mu2 is. Plus or minus, again, t star times our standard error here, s1 squared over n1 plus s2 squared over n2. Okay. So as far as creating confidence intervals go, I think plugging values into the formula is probably the straightforward and easy part. It really just comes down to reading the problem and correctly identifying what your values are, and then finding a upper and lower bound. Okay. Is this good? All right. And then so you know, the conclusions, you're basically looking to see if a particular value is within the bounds of your interval. So you know, if you've got, you know, for confidence intervals of one sample, so that's either, you know, for p or mu, you know, you might have a question: do we have evidence that the parameter, whether that's a p or a mu, is different from some value, let's say k, okay? And then so you're going to just see, you know, see if k is in the interval. K is within the interval or not. Okay, and if k is in the interval, okay, you will not have evidence that the parameter is different from k. Okay, so k is a plausible value at that confidence level, and so you won't have evidence that the parameter is different from k. And on the other hand, if k is not in the interval, you do have evidence that the parameter has a different value from k. Okay, and so that is that's that. And then again, in the kind of the video I've talked about some of the other conclusions you can make with confidence intervals. You know, if I ask, do we have evidence that the parameter is equal to some value j? All right, the confidence interval will never say that we have evidence that the parameter is equal to a particular value. It just doesn't do that, okay? All we can say is that this is a plausible value, so we can't reject it, but it doesn't mean that the parameter is equal to that value. Okay. And then if you're talking about a confidence interval for the difference between mu1 and mu2, the value that you're looking for there is 0. And then if 0 is in the interval, then it's possible for mu1 and mu2 to have the same mean. If 0 is not in the interval, then you have evidence that mu1 and mu2 have different values. Okay, and again, all of this, as far as this conceptual stuff goes, covered in the video. Okay. Are there any further questions about confidence intervals, or is there anything more that you want me to write up on the screen? We're good? Okay. All right. Then let's talk about hypothesis tests then. So as far as hypothesis tests go, we can kind of always cover them in the same maybe 4 steps. So step 1 will be create your hypotheses, of which we will always have 2. We have a null hypothesis that will always have an equal sign. And then the alternative hypothesis will always be identical to the null, except the equal sign is replaced with something else. Either a not equal, a greater than, or a less than, something like that. But always these two things should look almost identical, or they should look identical with the exception of the sign there, okay? Step 2, that's where we check our conditions. And as far as the test goes, I will have a few questions dedicated to just checking conditions, kind of like in the practice final exam. And as far as the actual problems where you're going to be doing calculations and stuff, it's safe to assume that the conditions are met for all of those problems. You don't have to take time to check the conditions there. But I do have a section where you will have to check the conditions kind of very much, and I actually had that section on midterm 2 as well. Most of you guys did fine. Some of you really struggled with that section. Like you got all of the questions right, except you got like 4 questions wrong, and they were all on checking conditions. Okay, and so if that sounds like you, make sure you can check the conditions. I think there was a lot of confusion about the big population condition, like there's like the M&M's problem and things like that. As far as the big population condition goes, this is a condition that is rarely violated, okay? Because in general, when we do statistical inference, it's because the population is too big for us to observe directly, and so we rarely run into the problem where the population isn't big enough, okay, for statistical inference. And this problem for the big population condition is really only violated, or if we know the actual size of the population is some limited thing. So like if we have like an institution or a school or a company where we know the size of the population, I would say that's really the only time we have to worry about having a population that's not big enough. If a problem doesn't specify the population, usually it's safe to assume that the population is going to be big. So when we're talking about M&Ms, the population there was all M&Ms in the world, which you know, I don't know how many there are. There's probably more. Do you think there's more M&Ms right now than people? I don't know. Probably, right? Like, I think like you just walk over to the candy vending machine. There's like whatever. Okay, lots. So billions of M&Ms. Okay, you know, taking a random sample of 4 candy bags is not going to be too big a problem with the big population. So. You know, and then always make sure that your sample is a random sample, things like that. Okay, so anyway, there's just a separate section there for checking conditions, but not part of the calculation problems, okay? As far as step 3 goes, this is your calculations, and for all hypothesis tests, they can kind of be broken down into 3 parts. Finding your standard error to kind of get an idea of how the sampling distribution, how much spread exists in the sampling distribution, because the standard error is kind of like the standard deviation of the sampling distribution. You know, if we assume that the null hypothesis is true, that's the standard error. And then once you find your standard error, you get a test statistic, which is, you know, the difference between the reality and the expectation, or always the observed minus the expected value. And then we take that difference and we say, you know, is that a large difference or a small difference in comparison to the standard error? So we divide it by the standard error and we try to decide, is this very different or not that different from what we expected? And then the last thing, once you get your test statistic, then you would look it up in the reference table. In a table, either the Z or T, to get a p-value, to get the associated probability. I'm having trouble writing. Get a p value here, okay? And then, so once you get your p-value, then you can make your conclusion. And as far as conclusions go, you know, if your p-value is greater than alpha, then we do not reject the null hypothesis. This means the data that we have is quite likely to happen when the null hypothesis is true. And so that means we do not have evidence to support the alternative. And on the other hand, if the p-value is less than alpha, we do reject the null hypothesis, and we do have evidence to support the alternative. And so I'll just kind of recap hypothesis testing for proportions and hypothesis testing for means. And I know a lot of this is already on your formula sheet, but I think maybe, I'm hoping, going over it here will just make you feel even that much more comfortable with using the formula sheet. So we'll start off with hypothesis testing for proportions. Okay, so the null hypothesis here is always going to be p is equal to some value p0. So it could be like, the null hypothesis is that p is equal to 0.25. It's equal to 25%. And then the alternative is always going to be exactly the same thing as that, except you just replace the equal sign with something else. You could have p is greater than or p is less than p0, whatever that value is. Okay, so these are all possible alternative hypotheses. And then as far as calculations go, our standard error is going to be P0 times 1 minus P0 over n, okay? And then so note that we use P0 and not P hat, okay? We use P hat in our standard error calculation for a confidence interval. For the hypothesis test, we use P0. And then our test statistic Z is the difference between the observed proportion that we have, P hat, the reality of our situation, versus what we expected if the null hypothesis were true, which was P0. And we're going to take this difference and divide by the standard error. Okay. And then whatever Z you have, you would look up your test statistic in the Z table. Okay. And then, so I'll cover this in just a moment. The process for hypothesis testing for two proportions is very similar. The null hypothesis is always P1 is equal to P2, or it can also be written as P1 minus P2 is equal to 0, which is, I think, how it appeared in the practice final. But these two things are saying the exact same thing. The alternative will be that P1 is not P2, or that, again, equivalently, P1 minus P2 is not equal to 0, or P1 is greater than P2, or P1 is less than P2. Okay. When we do our calculations, we have to first figure out our P hat, which is our overall proportion, x1 plus x2 divided by the quantity n1 plus n2. So we get our overall proportion, and we can use that to calculate the standard error for this problem, which is P hat times 1 minus P hat over 1 plus n1 plus 1 over n2. Okay. And then the test statistic Z here is the difference between our observed proportions, and that difference divided by the standard error. Okay. And then again, you would look up the test statistic in the Z table. And if the alternative has a greater than sign, then the p-value is the area to the right of Z. If the alternative has a less than sign, then the p-value is the area to the left of Z. And if the alternative has a not equal sign, then the p-value is the tail area, which is the area away from 0, times 2. So you'd find the tail area first, and then you would multiply that by 2. Okay, and then if you guys have this down, I'm going to flip to the next page. All right, and we'll cover hypothesis testing for means. Okay, and this is kind of our last thing. So hypothesis testing for mu. Our null hypothesis is going to be mu is equal to some value mu0, and the alternative is that mu isn't that particular value. So maybe the null hypothesis, so for example, the null hypothesis could be that mu is equal to, 42 versus it's something else, all right? Or, mu is greater than that, or mu is less than that, whatever it might be, okay? Your standard error is s over the square root of n, and your test statistic t is the difference between what we observed, x bar, what we are expecting if the null hypothesis is true, which is mu 0. We're going to take that difference and divide by the standard error. And then we would look it up in the t-table. Okay, and the way this works with degrees of freedom equal to n minus 1. Okay, and I'll talk about that. For hypothesis testing for two means, mu1 and mu2, the null hypothesis is always that the two means are equal to each other. Mu1 is equal to mu2. What's going on? Or equivalently, that the difference between them, mu1 minus mu2, is equal to 0. Okay. We can say that they are unequal, or mu1 is greater than mu2, or mu1 is less than mu2. All of these and their equivalent counterparts, right? Mu1 minus mu2 is not 0, or mu1 minus mu2 is greater than 0, or the standard error here, just a slightly more complicated formula, s1 squared over n1 plus s2 squared over n2. And then the test statistic here is the difference between our two sample means divided by the standard error. Okay. All right, and there again you look it up in the table with degrees of freedom equal to n minus 1. If you have two n's, you use the smaller of the two n's. And if the alternative has a greater than, then t should be positive. Okay, find the column headings corresponding to t. So you look up t in that degrees of freedom row, and then find the column headings to get your to get the p-value. If the alternative has a less than sign, t should be negative. Okay, ignore the sign and look it up in the column headings, okay? Ignore the minus sign, look up in the columns, and the headings are the p-value. Okay, of course you're going to have to figure out whether it's should be the less than or greater than. And then lastly, if the alternative has a not equal sign, okay, the sign of t does not matter. Just look it up in the t-table and go to the column headings and you multiply it by 2. Okay. Look up in table, and then the p-value is 2 times the column headings. Okay, and I think that kind of summarizes all of the statistical inference methods that we have covered in this class. Are there any questions on any of this stuff? Okay, it's been a great privilege being your teacher this quarter. You guys have been a great class to teach. I'm always excited to see you guys, especially those of you who smiled at me throughout the quarter. I greatly appreciate that. It's been a real privilege. I wish you all the very best as you guys study. All good luck as you study for your final exams. Be well and take care out there. So. Oh, if I could ask you guys.